Isn't it amazing? After a global effort and 100 years, we finally have observable proof of Einstein's theory of general relativity. Right, okay, but what am I even looking at here? I thought black holes were just these big scary things that like went around sucking up everything. Are we in any danger having taken a photo of it? And don't they suck in light? Like, how did we make an image of it? And what the heck are even black holes anyway? So in a previous video, which you can watch just now by clicking the card, I talked a little bit about star formation, how they're born, what happens during their life, and then what happens when the core collapses when they run out of fuel. And in pretty much all the cases that I talked about then, when the core collapses, it heats up until it gets to a point where the thermal pressure stops it from collapsing any further. Or in even bigger stars, sometimes that thermal pressure isn't enough to hold out all that mass, and so they collapse into a neutron star. These very hot, very dense stars are held together by what's called electron degeneracy pressure. This is pressure basically because electrons aren't very friendly, they don't like to be in the same energy levels as other electrons, and so as you squeeze the electrons together, some of the electrons get forced into higher energy states, pushing out that core until you get to a stable equilibrium. This electron degeneracy pressure works up to a certain mass limit, the Chandrasekhar mass limit. Now once you get above that mass, the electron degeneracy pressure isn't enough to stop the core collapsing even further. Above this mass limit, the core just continues to collapse until a force that we don't know yet might stop it. At this point of collapse, you get a super dense black hole, and the physics gets a little bit weird around it. So it's not a hole, it's a lot of mass crammed into a tiny space. In fact, if the Earth was made of black hole matter, it would fit into a teaspoon. So it's not a hole, but is it black? Well, it might be, but we don't know. There's not a lot that we know about black holes, and there's not a lot that we can observe about them either because they are so dense. Not even light can escape their gravitational pull. Wait. Light can't escape it. What do you even mean? Right, let me put it this way. All of space and time are linked by the speed of light. Now that's the fastest that anything can go. So that's the distance that you can travel in a certain time is always going to be linked. Now mass curves space-time. And so what we see is light curving along space-time until it reaches our eyes. So let me do my favorite thing right now and draw you a wee graph. So imagine we have space on the x-axis and time up the y-axis. And an event happens right here in the middle. And it sends out a bunch of light rays. Light travels at the fastest speed possible. And if you're here inside this shaded bit, then you can observe the event, right? In fact, if you are in the middle, you can be observed by everything up here. And you can observe everything down here. Now, heavy things warp space-time. They squeeze and they bend things. Now, really, really dense things will warp space-time so much that they have an event horizon. So that on the outside of the horizon, you can't actually see anything that happens beyond that horizon. When you approach the event horizon, your rays of light get pulled towards the mass so much that on the horizon, light just whizzes round and round. Inside there, nothing can escape. Not even light. Now it's this nothing can escape wording that has really intrigued sci-fi writers. And all across science fiction, black holes are always depicted as these big vacuums in space going along, sucking up everything around them, destroying entire planets and solar systems, sending them into oblivion, which is just not true. If you replace the sun right now with a black hole of the exact same mass, gravity wouldn't change. The Earth would stay on the same trajectory. All you would have is a black hole the size of Glasgow sitting where the sun should be. Things orbit around black holes like normal. And in fact, it's because of the way that things orbited around black holes that we even detected them in the first place. Every galaxy that we've seen has a supermassive black hole at the center of it. And every single black hole that we can detect, we think there's an accretion disk around it of all the matter slowly collecting over time. So an accretion disk is a large disk of matter, swirling around, slowly losing momentum as it collides with itself and falling into the black hole. And because there's so much gravity involved in in these things, the accretion disks are swirling really fast, like close to the light of speed fast, and are really energetic, like you're talking millions of degrees hot. So when scientists finally figured out a way to get a high enough resolution image of a black hole, what we expected to see is a hot accretion disk going nearly the speed of light with nothing or nothing observable in the middle of it. And that is exactly what we got. We got the Eye of Sauron. I am so excited about this amazing feat of science. It's life-changing. I'm amazed it's happened in my lifetime. I am lucky enough to have seen the Higgs boson, the first image of a black hole, the first detection of gravitational waves. Like, what a time to be alive! And all of this is truly paving the way for some amazing discoveries in the future. We can learn so much from being able to observe black holes. So what is this picture actually telling us? Well, if you look at the accretion disk, one half of it is really brightly coloured and the other half of it is a bit faded. Now that's because the accretion disk is spinning. Now remember that this accretion disk is travelling really fast, and when you start travelling close to the speed of light, you start beaming light in the direction of your travel. And so we're seeing more light from the matter that's coming towards us and less light from the matter that's going away from us. As the resolution increases of these images, we'll be able to start seeing the warping effects at the event horizon, which is going to be really, really cool, and I'm really excited to see where this goes. If you'd like to know more about how scientists made basically a virtual radio dish the size of the Earth to get a high enough resolution image of the black hole, then give this video a like and leave a comment down below and I'll definitely make a video on it. And you might have heard in the news about a woman called Katie Bowman who helped develop the algorithm that let us actually see the black hole. She was obviously part of an amazing team that put in so much work and effort into this, but as a woman in STEM, and that's something that I'm really passionate about, I might make a video about her as well, so let me know if that's something you're interested in. Anyway, I hope you enjoyed this episode of Science with Steph. If you did, give it a like and share it with your friends, and in the meantime, if you want to watch my last episode on the evolution of stars, you can click here, or you can watch the video that the YouTube algorithm thinks you'll enjoy best by clicking here. Alright, thanks for that, and I'll see you next week. Alright, bye!